Welcome back to this third video on sample presentation of statistical test results in RStudio. In this video, I'm going to focus on presenting summary statistical test results for the pair T test and the Wilcoxon test. So I'm going to be looking at dependent samples. So you're going to have a within subjects factor that has two levels. As I would have mentioned in the previous videos, I suppose the purpose of these videos is more just how to present the statistical test results as a suggestion of it. The video won't be kind of necessarily going through what's happening behind the scenes for all the statistical tests or the lead up to the statistical test, even though I will run off the script for, I suppose, checking whether or not assumptions are met or violated and actually compiling the test and the corresponding effect size. But I won't necessarily explain, look, what's actually happening behind the scenes and what do all the results really mean. That wouldn't be the purpose of this video, but if it's something of interest, I'm more than happy to actually put up a video at a later stage. If people wanted to maybe comment below that they would like more information, I'm more than happy to facilitate. The motivation for doing these videos is often what I find is that when I do facilitate training courses in statistics, that a lot of the time is spent on, I suppose, talking about the appropriate descriptive statistics and statistical inference that will be deployed depending on the type of data that you have, how to actually do that in RStudio, and how to interpret the results. That often there's not a lot of time spent on how maybe potentially to present the results, that if you're looking at presenting your results in a table for a paper or for a thesis, how do you actually get the results from RStudio into to a table kind of format. I'm not a fan myself of copy and pasting things. I'm not a fan of I suppose creating tables manually. I much prefer there being a track record of the process, if at all possible. Okay, and I suppose ultimately that's the main motivation for doing these set of videos. Okay. The data that I'm going to look at here for this one is, so this is the data set that we would have defined or created in a previous video, and here's the link to the video. This is looking at the triglyceride measurements of 16 patients across 5 time points where we have males and females. It's worth just noting that all these measurements here are just randomly selected, so this is not in any way real data, but it'll kind of work for what we need for the purposes of this video. So we're looking at a within subjects factor with 2 levels. So I think what would be fairly clear cut is we're going to just look at comparing baseline against 1 month, the triglyceride measurements. Triglyceride measurements, the unit will be milligrams per deciliter. And I suppose just to add an additional line more for the kind of the script and to using the dplyr package, I'm just going to focus on the males. So I'm going to focus the males baseline against the males, males at 1 month, the triglyceride measurements. Okay. So if we go to the RStudio script that we have, so you would have seen in the first video here that, so this is the third part obviously to a set of videos, that in the first part I would have outlined the various statistical packages that were going to be used for this. So you can see underneath the description to this video that there's a link to a Google Drive. From that link you will find that you'll have that Excel file that I was just showing you there, along with a copy of all this script here, if you find that what I'm presenting here is some way of use. Okay, so the first thing is I'm going to look at the data that was in Excel. When I imported it, I'm calling it long. I'm going to focus on the males only, and at the time point of baseline in 1 month. So there's 9 males. So 9 males over 2 time points should give us 18 data values. So that's what I'm going to just do here for the first line here. Then for the next bit then is I'm just going to look at, actually if I just run this off here, just the males here, you will see here for the males that the data frame, you have the 9 participants, you have the male variable, then you have your 2 timelines, and then you have your triglyceride measurements. So I just feel that it's just nice to have a concise data frame, kind of as tidy as possible. So I don't need that male measurement because it's basically just saying everyone is male. So that's what the line 192 here is just doing. It's just looking at just, I suppose, using the select function just to kind of tidy up the data frame a small bit. So this is where we now have the 9 participants across 2 time points. So we have 18 measurements. Okay. So then the next thing then is, even though this is kind of a very kind of getting to the end results kind of video, it's still kind of good to have a picture in our mind to what type of data do we actually have. So I'm just going to do a box plot to this. If I zoom in on this box plot here, we're looking at the triglyceride measurements, the change in triglyceride measurements from 9 males from baseline to 1 month. You can see here for what RStudio has done with the timelines is it's just kind of done it in alphabetical order as opposed to kind of chronological order. Like baseline here should be the first box plot. That's just down to explicitly defining the factor. So I'm actually going to just do that here. I just think for the, even though that this is kind of a crash course, it's still good to kind of be doing things right. So I'm just going to define the factor. I'm going to run that plot off again, and then I'm going to run it off a second time. I would have said in previous videos that generally I run off plots 2 times. Once is nearly the default version, and then the second time is just the tidied up version. So this is where we actually have it. So now we can see that our timeline is actually in order. We can see that triglyceride measurements seem to decrease over time for the males from baseline to 1 month. They have decreased. Is that decrease statistically significant or not? That's where we're going to try to do this, the test to apply. What test do we apply will depend on whether or not our data is normally distributed, okay? So we'll just go off and do that. So I'm just going to check for normality using kind of the same approach that I would have outlined in the previous videos. I'm just looking at the mean, median, the skewness, and then doing a test of normality. I won't dwell too much on this now because I've spoken about these in the previous videos, and what we can see here is that basically our data is normally distributed, so we can go off and do a paired t-test in confidence. The script that we're going to use for the paired t-test is very similar to the script that we used in the previous videos. All that's really different here is we're saying down at the very end, paired equals t. T being true. If you said false, then you'd be running off an independent t-test, and it's important obviously to distinguish between them, because the test statistic that's happening behind the scene is different for an independent t-test and a paired t-test, so it's very important to distinguish between the 2 types. Here, when we run it off, this is what we get. Now, what we're mainly interested for the purposes of this video is the p-value, the confidence interval of the differences down here, and then we're looking at what is actually the difference between the 2 time points. That's where we're mainly interested for the purposes of this video. If you'd like more information to maybe kind of to explain what's happening behind the scenes for this, by all means throw something into the comment. I'd be more than happy to maybe respond to the comment if it can be responded in one go, or generally put together another video if it's of help. No problem whatsoever. So here what we have in this case here is we can see in our case here that the p-value is greater than 0.05, so that would tell us that the difference that we're observing in that box plot is statistically insignificant. If it was significant, we could be interested to look what is the strength of the result. Even if it's insignificant, we could say, look, we've only a sample size of 9 subjects. If we work out the effect size and then try to do a power calculation, we might be able to look at, if we increase our sample size to a certain number, that the difference that we're observing will be statistically significant and so on like that. So working out the effect size of results can sometimes be beneficial. So that's what I'm just going to do next here. I'm just going to work out the effect size using the RStatics package, and then using the Cohen's d function within that. So this will give me effect 3.1 is what I'm calling this. We can see here that the effect that we're getting back, so this is the Cohen's d classification. So this is where you have the 0.2, 0.5, 0.8. So our difference here is in the point between 0.2 and 0.5. So it would be, sorry, between 0.5 and 0.8. So it would be classified as a moderate difference. Then, similar to now the lines of code that I would have used in the previous videos, okay, I'm just going to isolate what the effect size value is to 2 decimal places, and then I'm just going to put an actual classification on it. How would I like to present the result? And this is how I end up doing it, okay? So you can kind of look through this kind of script here yourselves if you want, obviously in your own time, but basically we can obviously see that our result should be classified as moderate, and I find that this script is just a nice way of, I suppose, pulling the bits of information together. Then, similar to the previous videos, and I know I say that a lot, but I think often what I try to do when I'm especially getting my head around doing something for the first time is try to keep to the same structure. I find that a help. Okay, so the results that I'm suggesting to present as summary statistical test results will be the mean difference, the confidence interval of the difference, the p-value, and then the effect size. Now you could say you want more, you might want less. You could say, look, you don't want the confidence intervals, then remove it. You could say you'd like the test statistic, you'd like the degrees of freedom, then you can include them. Okay, you can see here underneath how I'm actually just, I suppose selecting the particular values of interest using the kind of the dollar sign, the kind of that attribute kind of function, and that's very good for isolating a certain part of an output, okay, and that's ultimately what we're just using here numerous times, okay. So the first bit here is, look, where I'm taking the result, res 3.1, and I'm looking at the estimate, which is basically what is the difference. Then I'm looking at the confidence interval of the difference, the lower, by doing the square brackets 1, the upper, and then the p-value, and then the effect size, okay. So this is what we actually have. I'll just run that off. I never ran off the label, sorry, so I'll do that, look, in order like this. Then I'm going to put them together as a data frame, and these are the results. So what we can see here is the mean difference in triglyceride level measurements from baseline to 1 month is 21.2 milligrams per deciliter. Then we have confidence interval of the difference, which contains 0, so that suggests that no difference exists. The p-value is greater than 0.05, so which means that the difference that we're observing here at the moment, if we're working off a 5% level of significance, is statistically insignificant. But we can see from the effect size here that our effect size is actually moderate, so the standardized mean difference of what we're observing is actually a moderate difference. So maybe that could motivate us to go off and gather more data. We might do a power calculation to determine how much more data do we want to use. If you look here, we have a size of 9, so this is like a pilot study really, that we might be using the results here to actually inform a future study. Then the last step then will be just writing those results to Excel. So this is the output 3.1. So these are the various outputs I would have generated in the previous videos. Here's output 3.1. I won't format the table, but here's the results that we actually have, okay? And just what I like with doing this, and I'm not saying that this is all the information you need. You might want more information. I'd assume before these are the test statistical results. So before this, in your own research, I'm assuming you're presenting your own descriptive statistics and so on like that. The purpose of this video is just looking at the statistical test results. This is just a guideline. You might want more information. You might want less, but hopefully you can maybe kind of use the script that I'm showing you here in the video as a starting point. The last thing for this video then will be just the kind of the what if scenario. And like ultimately, when we look at the data that we have here for this case here, we were perfectly correct to do the paired t-test. But when you're looking at your own data, you might find that your data is not normally distributed. You might find that you need to do a non-parametric test. So I just want to show you the script to doing a non-parametric test. Now I'm going to use the same data that I did here for the paired t-test. So this Wilcoxon test, the script I'm going to use there is more for illustration purposes. It's actually not required for the data that I'm actually looking at, because it actually satisfied the condition of normality, and using the paired t-test was actually reliable, okay? So it is really just for an illustration purposes. Now you could say, look, that you might transform your data and then do a paired t-test. That's for you to decide, okay? So, but for this, the purpose of the video, I'm just trying to show a parametric test result and a non-parametric test result, okay? So this is a what if scenario, so we actually don't really need it here, but anyway, I will do it nonetheless. So in this case, and this is the same kind of package that I would have used before, the RStatics package. Here I'm using the Wilcox test. This is very similar to the script that I would have shown for the independent t-test in the part 2 video. All that's different here is down at the very end, I'm saying paired equals true as opposed to paired equals false. If it was paired equals false, then that's kind of the Mann-Whitney-U test that you're generating. Paired equals true is the Wilcoxon test. If you run that off here, what it gives you at the far bottom left is the median difference. Then we actually have the p-value, and then we have a confidence interval of the difference, and they're kind of the three of the results that we're interested in. The last result is just to work out the effect size. So then that will be working out the Wilcox F size using that function. This gives us a large effect size. That's what this is telling us here. If we're looking at the data not being normally distributed, this is just we didn't actually need to do this in this case here. So then I'm just going to follow the kind of the same model that I did the last time, of where I'm looking at the effect size to 2 decimal places, then classifying it in my own format of negligible, small, moderate, or large. So in this case here, it's being classified as large, okay? And then it's just looking at presenting the results. So the median difference, the confidence interval of the median difference, the p-value, and the effect size. So the same steps as before. And you can see here the similarity with the previous script, okay? So there's very little difference. And I'm just going to quickly just highlight all that. I'm just going to write it straight to Excel. Okay, here you can see the results. But I'm just going to see here, look, it's in Excel as well. And here are our results again. Okay, so it's just to kind of come up with a structure that can be useful. So we have the median difference of 24.5. We have the confidence interval of the difference, which contains 0. The p-value is greater than 0.05. So that would then mean in this case here that this would be seen as a large effect size. Okay, so that brings us ultimately to the end for this here. Hopefully you find the videos of use. Here are some contact details if you wanted to reach out, if you had any particular questions. But I would encourage people putting some comments into the comments below. If you find that the videos are of use and of that helped you, it'd be great if you liked and shared the videos. Equally, subscribing to the channel would be a big help, and by subscribing to the channel, obviously you'll get notifications then when newer videos are uploaded and everything like that. Okay, so I hope this helped, and so for the moment, all the best. Bye bye.